Hey there, welcome to our lesson 6-1 first practice problem. This video is our full practice set. This first question says that a 75 kilogram firefighter climbs a flight of stairs 28 meters high. How much work does he do? All right, so because it only gives us the displacement vertically, 28 meters high, then we're just going to be calculating the work vertically. And so just a reminder, our formula for calculating work is going to be equal to the force times the displacement. And the way that we're going to find out how much work is required is we're going to find out what forces are already acting on this firefighter. Okay, so the only force, because it doesn't exactly tell us anything else, the only force we know is working on him is gravity. So that force due to gravity is going to be equal to his mass times the acceleration due to gravity, which is going to be equal to 75 kg times 9.8 meters per second squared. All right. So if we go ahead and pop that into the calculator really quick, we got 75 times 9.8. And we're going to have force due to gravity of 735 newtons. All right. So now that we know how much force we need to counteract, okay, then we're going to apply that force to our firefighter. And then we're also going to see how much distance they're going to travel. So the work is going to be equal to 735 newtons times the distance that we need to travel is 28.0 meters. All right. So then if I go ahead and multiply my 735 by 28, then I get my work, which is going to be in joules. Newton meters is joules. All right, and that's going to be about 20,580 joules. And that's how much work the firefighter is going to need to do in order to get up 28 meters of stairs. All right, guys, good luck. See you in the next one. Here we have what is the minimum work needed to push a 950 kilogram car 710 meters up along a 9-degree incline. Ignore friction. All right, well, that's pretty nice that we get to ignore friction, but what we're going to go ahead and start with is a free body diagram that represents a ramp. Well, it's almost very ugly. All right, and this ramp is going to have an incline of 9 degrees, 9.0 degrees. I'm going to go ahead and draw a box on this incline that's going to represent our 950 kilogram car. All right, that box is going to have some force due to gravity that's always going to be applied to it vertically downward. All right, so I'm going to go ahead and label that. And that is going to be the force due to gravity. It's going to be equal to the mass of the car times the acceleration due to gravity, which is just mg. And then every time I'm on a ramp and I'm dealing with some gravitational force, then I know that I have to also consider the components that are contributing to normal force and to the gravitational force that's horizontal to the surface of the incline. So then I end up drawing this little triangle. And remember, this can be a little bit tricky, but the triangle is going to always have the force due to gravity as the hypotenuse. So that should help you out. So that means the right angle should be here. That tells you the part that's going to be opposite to normal force. And then also it'll give you a leg that is horizontal to the surface of your incline. All right, so we're looking for really that leg that's horizontal to the surface of our incline. And that's just because we're dealing with a work problem here. And normal force is generally, especially in this case, perpendicular to our displacement. So it's not going to actually be doing any work, and it's not going to be affecting the work required to do anything here necessarily. It does, kind of, if there was friction, it would affect the work a little bit, but we're not considering friction. That said, let's just go ahead and find that opposite leg to this little right triangle we've made. And we know that in this right triangle, we have the same angle here as the incline, so 9.0, right? And so then that opposite leg is then just going to be mg sine theta. All right, so then we know that the component of gravitational force that is actually pulling the box down the ramp is mg sine theta. So that is perfectly horizontal and parallel to the surface, or not perfectly horizontal necessarily, but it is parallel to the surface of our ramp. So mg sine theta. And of course, theta is 9 degrees. All right, so we want to know how much is the minimum work needed to push this guy up this ramp 710 meters. All right, so because we're just looking for the minimum work, we only need the force applied that actually balances out the force due to gravity that's parallel to our ramp, right? So what I'm saying is that, yes, if we set an applied force that's equal to mg sine theta, then technically our object would be in balance, but we're talking about the minimum work. So any amount of force greater than that would actually start to move the box up the ramp. So indeed, the value that we're going to be looking for is not the amount of joules that we necessarily need, okay? Not the amount of joules of work that we necessarily need to do, but it is adjacent to the absolute minimum value, okay? So any amount of more joules would cause there to actually then be a net force up the ramp, and that's what we're looking for here today, that point when our forces are equal and balanced, because that's giving us the value that's adjacent to our minimum amount of work required. All right, hopefully that made sense. If I said that a little bit weird, go ahead and ask me about it in the comments. I'd love to reword that a little bit. But what we're doing here is we're looking for the work, okay? The work, when of course it's equal to our force times our displacement, all right? And we're going to be talking about a force that we're going to apply parallel to our surface. So we don't need the cosine theta here. We don't need the cosine theta here because we're kind of inventing our own force. So we can say what direction it's going to be in. So it's going to be parallel to the positive x-axis. And of course, guys, remember, when you're drawing a free body diagram, you do want to kind of give yourself your xy axis somewhere on the screen so that you can see what direction is positive, what direction is negative for that specific problem. So then we know exactly the minimum amount of force required to start this box moving up. It's going to be that mg sine theta because that's what is pulling it down in the first place. So we're going to say that the minimum amount of work is going to be equal to mg sine theta times our displacement. And we know all of these values. We know the mass of the car, we know the acceleration due to gravity, we know theta, and we know our displacement. So at this point, it's just a matter of plugging in and calculating our values. So work is going to be equal to 950 kg times 9.8 meters per second squared times sine of 9 degrees, and then times 710 meters. All right, if you plug all of this into your calculator, you're going to get a value that's about 1 million. It's just over 1 million. And because we have to be careful of our significant figures, we're just going to take that to 1.0 times 10 to the 6 joules. All right, so that's going to be the minimum amount of work required to get this car moving up this ramp and to get it a distance of 710 meters. All right, guys, good luck. I'll see you in the next one. Welcome to the third problem in our lesson 6-1 quantitative practice set. A grocery cart with a mass of 16 kilograms is being pushed at constant speed up a 12-degree ramp by some applied force F sub P, which acts at an angle of 17 degrees below the horizontal. Find the work done by each of the forces, the gravitational force, the normal force, and this applied force on the cart if the ramp is 7.5 meters long. Now, I do want to point out one very important part of this question before we start doing anything. It's the fact that this cart is being pushed at a constant speed. And we discussed in our lecture that if an object is moving at a constant speed, then there is no acceleration, and therefore there should be no net force on it. And if there's no net force on it, then the net work should be zero. And that's true. The actual net work on this object is zero simply because it's moving at a constant speed. But that doesn't mean that each bit of the forces that are acting, because there are multiple forces acting, it doesn't mean that each one might not be causing some work that is just being canceled out by one of the other forces. And that is exactly what is happening here. One of our forces would be causing some work if it weren't for the other force doing negative work, canceling it out and causing no net work to be done. So let's go ahead and draw a free body diagram to try to figure out what's going on here. So in blue, I'm going to go ahead and draw a very large ramp so that we can see very clearly the forces at work. All right, and then I'm going to go ahead and draw a box that's going to represent our 16 kilogram cart. Now, this is our 16 kilogram cart. Let me get my pen. And there are three forces that are being applied to it. All right, so in green, let me go ahead and show you the force due to gravity, which always works vertically downward, okay? And that is going to be my mg, okay? In purple, let me show you the normal force because that always works perpendicular to the surface. And so in this case, it's going to be pointing in this direction. This is my attempt at perpendicular to the surface of the ramp, and we're going to call this F sub in. Okay, it has a direction, of course. And then one more force I'll do in orange is actually working at 17 degrees below the horizontal. So if I'm going to draw a line that represents the horizontal, it's going to be this dotted line here. This dotted line represents almost perfectly horizontal. So our applied force in orange is going to be 17 degrees below that. Okay, I'm going to go ahead and give us a vector arrow here that's going to represent our applied force, F sub P, and it's going to have some angle that is 17 degrees. All right. Now, one more thing to mark, of course, is the fact that this ramp has an angle here that is 12 degrees. And now we've labeled all of the forces that are actually being applied to this box. That said, the thing is that we know that our displacement is actually in the positive x direction up this ramp. So let me go ahead and kind of write my axes really quick. So that's x, that's y. We know that our displacement is in the positive x direction up this ramp. So now we need to figure out a little bit about what angle our forces are acting with respect to our displacement, because that's going to be important for us to find the work that that specific force is doing on our box. So one thing you'll notice right off the bat is that the normal force actually, because it's perpendicular to the surface, has a 90-degree angle and is perpendicular to our displacement. So that means essentially normal force is not going to be doing any work here. So we can go ahead and say that F sub in is already doing zero work. So let's move past that really quickly and let's start talking about the force due to gravity and the applied force, because neither of those are perpendicular. So left alone, they should be doing some work on our cart. In order to figure out how much work, we're going to have to figure out what angle they have with our cart. That said, we can very easily find out this angle really quick, the angle that our applied force has with our displacement, because we know that the displacement has a 12-degree angle with the horizontal, a 12-degree angle above the horizontal, and our applied force has a 17-degree angle below the horizontal. So that means that our force, applied force, has an angle of 17 plus 12 degrees with our displacement. So in other words, an angle of 29 degrees. And I can actually label that really quickly. I can label that really quickly with orange. Okay, so let me put that angle here. It's going to be a 29-degree angle. All right, and then now we have to decide what is the actual component in the positive x direction. So the way that I'm going to do that is I'm going to go ahead and I'm going to draw some imaginary right triangles so that we can get the right triangle trigonometry correct. And that right triangle needs to have my applied force as the hypotenuse. So what I'm going to do is I'm going to make a 90-degree angle with my displacement. All right, you see there? So I have a 90-degree angle with my displacement, so I can find the leg, I can find this leg, and that's going to be equal to the component of my applied force that is parallel with our displacement. Fantastic. And the fact that we know this angle is everything, because then we can say that the actual component that's parallel to our displacement is going to be the magnitude of our applied force, okay, times, and because this leg is actually adjacent to our angle, we're gonna use cosine of 29 degrees. Okay, that's fantastic. So this is a really important part to have gotten to, because now we know exactly how much of our applied force is going to be parallel to our displacement. So this is the force that would actually be doing work. So this is the force that we would actually plug into our work formula. The work being done by F sub P, okay, should be then equal to F sub P, the magnitude of F sub P, of course, times cosine of 29, times the displacement. All right, so this is what we want to figure out. All right, this is what we want to figure out. Now, here's the thing is that we don't know what the magnitude of F sub P is, okay? So we need to figure out some information about F sub P first, and the way that we're going to do that is we're going to take into account the fact that the net forces on this object are 0. That said, let me go ahead and write out in math form exactly what I mean by that. So let me move all of this stuff a little bit over so I have a little bit more room to work mathematically. Let me say that I know that my net forces are equal to 0. And so let me write that really quick. F net in the x direction is equal to 0. And I know what those forces are. So this is the sum of my forces, right? So I know what those forces are. One of them is going to be F sub p cosine of 29 degrees. And then another one is going to be, and because it's working in the negative direction, and we've done this before, all right, we've done this before, let me show you. All right, one of them is going to be, because this is the same as the angle on our ramp, one of them is going to be mg sine 12 degrees, because that is going to be this leg, the leg that's parallel to the surface of our ramp, but in the opposite direction to our displacement. So that means that what I'm saying is that the component of our force due to gravity that is working against our displacement is mg sine 12 degrees. All right, so that's going to be working in this direction. All right, so these two together must be canceling each other out because our box is moving at a constant speed. So I can say that these two things are equal to 0. And the great thing about knowing mg, because we know the acceleration due to gravity and we know the mass of our box, is that we can actually solve for a magnitude of our applied force because we know everything here except for our F sub p, the magnitude of our applied force. So then what I'm going to go ahead and do really quickly is I'm going to rewrite this equation a little bit. All right, it's going to all be in blue now. It's going to be that F sub p cosine 29 degrees is equal to mg sine 12 degrees. All right, awesome. From there, I'm just going to go ahead and isolate the magnitude of my applied force. It's going to be F sub p is equal to mg sine of 12 degrees over cosine of 29 degrees. So that's fantastic because that's a value. You know, assuming we have our calculator, that's a value because we know that mass is 16 kg. We know that gravity is 9.8 meters per second squared. We can calculate sine of 12 degrees and we can divide it by cosine of 29 degrees very easily. All right. Now, that said, let's go ahead and move some of this work up so that we have a little bit more room to work. All right. That said, now that we have a value for F sub p, we can go ahead and take this value, okay? We can plug it into F sub p here to find out exactly how much work is being done, okay? Because we know our displacement as well. Our displacement is just 7.5 meters long. All right, so I'm gonna go ahead and say that W, the work being done by F sub p, is going to be equal to mg sine of 12 degrees over cosine of 29 degrees, okay? That's the magnitude of our F sub p, okay? That's the magnitude of our F sub p. We're gonna multiply that by our displacement, okay? And then, of course, because of the fact that our F sub p is not pointing perfectly with our displacement, we're then gonna have to multiply that by cosine of, remember, because we still need our cosine of our angle theta between the two. In this case, it's theta plus, it's 29 plus 17, cosine of 29 degrees. Okay. Oops, 29 degrees. All right, so just to clarify here, we have our work formula, but just focusing on the work being applied by the, being done by our applied force is equal to, this is F sub p right here, okay? So this is F sub p right here. Okay, this is times displacement times cosine theta. And in our case, theta is actually this angle here. This angle here, the 29 plus, or not the 29 plus 17, but the 12 plus 17, which gives us 29. Okay, so that goes to that goes to this, and this whole thing, which we calculated here, goes to our applied force. So this is just the work formula. Now, when you calculate this, this is going to give you how much positive work that our applied force is doing. And because we know that the net work is 0, then we know then that our work done by gravity in the opposite direction, the work that's being done by this force right here, is then just going to be the negative same value and magnitude as our work done by our applied force. So really quickly, if you calculate all this out, if you calculate all of this out right here, what you're going to get is 244 joules. Okay, you'll get 244 joules, and that will be the answer for the amount of work that the applied force itself is doing. And we know that the normal force isn't doing any work because it's perpendicular to our displacement. But then you can just deduce, using your own conceptual reasoning, that because the net work is 0, then the work done by mg must then be negative 244 joules. All right, guys, there's a lot of steps to this problem, and there's a lot of conceptual math going on, and there's a lot of being able to actually draw a free body diagram and understand what direction forces are working. Okay, guys, so if you need to kind of play that back, or if you have a few questions about how to answer this problem, I'd be happy to maybe show a different approach, or just maybe just use different words in going through. Just let me know in the comments. That said, good luck.